let's get started. So, we're just continuing from where we left off in the previous lecture, where we are just reviewing the things from modules 1 to 5A, and pretty much we are now at module 1 that we are discussing. Okay. So, module 1 we actually started with talking about plug flow reactors, continuous reactors, batch reactors, and tried to show the equivalence between plug flow and CSTRs and equivalence between batch reactors and plug flow reactors. Then we took the example of a conveyor belt in order to do those analogies. Okay. Yeah, this is a several list of reactors that you came up with. Okay. Just be aware of all of the different types of reactors you had come up with, and we have discussed, you might have encountered in the past. Okay. Yeah, then we talked about stoichiometry. Okay, stoichiometry is something that you are very familiar with. This is something that from school days you might be doing. Just the difference is that we are now doing this in a very formal manner, and what we said is your nu Kj is the stoichiometric coefficient of kth species in jth reaction. Okay. So, let us say the reaction was N2 plus 3H2 giving 2NH3. Okay. Then the stoichiometric matrix is, and let us say the species that we are talking about are N2, H2, NH3 and something else. Okay. Usually when we do those reactions, we will add some amount of diluent in lab reactions. When it is large scale reactors, there might be some impurities that might be present. For example, hydrogen comes from reforming, so there might be some amount of carbon dioxide, some amount of methane and all that, which will not undergo these reactions. So, we have just put that as x. Okay. So, the stoichiometric coefficient is -1, -3, +2 and 0 in this reaction. So, because of this, the matrix is going to look -1, -3, 2, 0. Okay. This is reaction 1. Okay, and these is species N2, H2, NH3 and your diluent, and let us just put it argon. For example, in our reactions that we do in our lab, we will use argon or helium as the diluent. Okay. So, those will be the overall species that will be there, and this forms the stoichiometric matrix. Okay. If there are multiple reactions, for each reaction additional column comes in this particular matrix. Okay. Yeah, and this is what I talk about. Now, we have talked about extent and conversion and rate of reaction. So, with respect to extent and conversion, okay. So, again, I mean, they have their formal definitions, but overall what I talked about extent, we will use the concept of extent, okay, in jth reaction in order to simplify our calculations. Okay. So, although it has a very specific definition as far as this course is concerned, and as well as a lot of things that you do in the initial part of your research, if you use extent, that is simply because it is a very convenient tool to use it. Do not worry about the formal definition too much. Okay. So, and I will come to that when we are talking about equilibrium. When it comes to conversion, So, conversion is for a species, extent is for a reaction. Okay. So, sometimes it is convenient to, to work out your equations in terms of species, sometimes it is convenient to work out in terms of reactions. So, whichever way it is convenient, you use extent and conversion. Okay. So, the definition of conversion is for any flow system it is Na in minus Na out okay. So, what do you really mean by Na in and Na out? Not really moles in and moles out, it is moles per unit time, right. So, not really Na in, but what should be there is Fa in and Fa out, okay. So, that is the definition of conversion, okay. And Fa is nothing but Q multiplied by Ca, okay. And this is the mole fraction. Okay. Mole fraction is also equal to Ca divided by summation of Ck. Okay. Why does this work? Because you can multiply and divide the numerator or multiply the numerator as well as the denominator with Q. So, if or in this case if you divide by Q, you will get Ca in the numerator and Ck summation of Ck in the denominator. Okay, that is how this works. Okay. So, now just an example with respect to how you can use. So, let us say you had a reaction A going to products, okay, and we had some rate of reaction. Let us say R was given by Kca divided by Ks plus Ca, whatever, this is Michael-Menten type of mechanism. Okay. So, let us say for argument's sake, and let us say this was carried out in a CSTR, right. So, for CSTR what we do is 0 equal to Q Ca in minus Ca plus RAV, right, and RA is just going to be negative okay. Now, you can solve this equation directly in Ca terms and get Ca as a function of Ca in, or you can say okay. So, then using this becomes 0 equal to Q multiplied by, so Ca in minus Ca is going to be and you can solve this in terms of XA and get it. Okay, that's also possible to do. Okay, that is how you would have studied design equations in your undergrad. Okay, and oftentimes design equations would have been given to you as first order, second order reactions, so you can directly substitute and do it, or you can do it graphically. Okay, this and this are exactly the same. There is absolutely no difference between the two. If you use the first equation, you will get the result in terms of Ca. If you use the second equation, you will get the result in terms of Xa. Xa can easily be calculated from Ca, and if you plug in all those values, you will get the exact same conversion. Okay, because there was a question later on saying that, oh, in our undergrad we did it in this particular way. Yeah, it does not matter. Okay, if you want to do it in terms of extent, that is also possible. Okay, the math will just get a little bit more complex. So, let us say that the extent of reaction was zeta. Okay, so the number of moles in the reactor is going to be, you know, Ca minus zeta, Ca in minus zeta. Okay, and then you substitute it and do it, and the math will get a little bit complicated. Okay, but the question that if you ask, can I do this or not? Yes, you can very well do it. Okay, if this were reversible, no problem, you will need also the concentration of P. If you are using concentration terms, right, if you are using concentration terms, you will have two equations and two unknowns, Ca and Cp. If you are using conversion terms, you will have one equation and one unknown. Okay, if you remember undergrad, if you had one single equation, you did either of those ways. If you had reversible equation, you used Xa. If you had series equation, you would again use Ca. If you had parallel equation, you will use Xa. If you have series parallel equation, again you will use Ca. No need of all of that complication. Use whatever method works for you. Okay. When it comes to multiple reactions, the method that works most commonly or most broadly is either concentration based approach for chemical engineers. If this was a mechanical engineering class, everything will be converted into mass fraction, and they will be doing everything in mass fractions. Okay. One of the nice things about using mass fractions, and again you can work it out and find out that if you remember, the first thing that we did in the first week of the class was to show that mole fraction in minus mole fraction out divided by mole fraction in is not equal to conversion, remember? Okay. However, mass fraction in minus mass fraction out divided by mass fraction in is equal to conversion. Why? Because total number of moles is not conserved. Ammonia reaction, the total number of moles is not conserved, but the total mass is always conserved. So, if you multiply mass fraction in minus mass fraction out on the top with mass flow rate, it will become mass flow rate in minus mass flow rate out, and denominator also mass flow rate in. Okay, and therefore, only with mass fractions the conversion equal to mass fraction in minus mass fraction out divided by mass fraction in works, not with mole fractions. Okay, so that is the reason why you know, mechanical engineers, because of the history in which mechanical engineering has evolved, use mass fraction. Okay, the history with which chemical engineering has evolved is a little bit different, and therefore we tend to use concentrations. Okay, there isn't a right or a wrong way. Okay, one way might be more convenient than the other. As long as you use the definitions and the overall concepts correctly, you can use whichever approach. Okay, but if you have a complex network of reaction, you won't be able to use zeta and x approach. It becomes fairly complex, but that doesn't mean it's not being used. For example, Professor Sridhar's research, one part of Professor Sridhar's research is on converting everything in extent basis, because number of species typically are much larger than number of reactions for the type of systems he works on. For the type of systems we work on in our research, we have something like 25 species undergoing 100 reactions. Okay, so for us concentration based approach is more convenient. For him, he works with 20 species undergoing 3 reactions. So for him extent of reaction based approach is more convenient. Okay. Are the two approaches different? If we are careful, they are not different. Okay, they end up being different because we make certain assumptions and then we will forget later on that assumptions are made. Okay, but otherwise whichever approach you use, that's perfectly fine. Okay, and again you will see again in your textbooks for equilibrium, oftentimes people would have used extent based approach, but for reactions they would use conversion based approach. Again you can very well use, instead of extent you can very well say conversion is so and so. Okay, that's also perfectly okay. Okay, and what happens when you use conversion instead of extent? Okay, you end up calculating the final rather than the calculating the formed part, and initial minus final will give you how much is formed. That's all. So in one approach you have 3 rows, you fill row 1, then row 3, then row 2. In another approach you fill row 1, row 2, row 3. Doesn't matter. Finally what you are trying to do is express the equation in terms of one unknown, whether that unknown is zeta or that unknown is x. Having said all of that, if you ask me a question right now, what approach should I use in the exam? I would suggest looking at how we have gone about in this course, use an extent based approach. Okay, does not mean that the other approach is not right. So if you are more used to your gate type things where you use conversion based approach, you can very well use conversion based approach. Okay, when I first taught this course, I taught everything in concentration based approach. None of the books had the concentration based approach, and then I converted everything in extent based approach in the third time that I taught that course, and that came to yesterday what we were discussing, just day before yesterday, just outside class, is which book to use and all that. So I have converted everything to extent based approach so that it is aligned a lot more with Davis and Davis book. Okay, but my personal preference is to work in terms of concentrations or in terms of mass fractions. Okay, so if any of my students is working on a system in complex geometry, we will use mass fraction based approach. If we are working on a system in ideal reactors, PFR, CSTR or batch reactors, then we will use concentration based approach. We usually do not use any other approach simply because it's just not convenient to use any other approach. Okay, so that's about research and how this connects with research. Okay. And we looked at the plug flow reactor, and this is the plug flow reactor balance that we have, and this is the well mix reactor balance. Okay, well mix reactor balance is applicable for batch, semi batch and continuous stirred tank reactors, all three. Okay, in batch reactors, this term is present, these two terms disappear and reaction term will be there. In a steady state CSTR, this term disappears, these two terms are there, this term will be there. In a semi batch reactor where reactants are continuously added or something else is continuously added, this term will be there, this term will be there, this term will be there, but there is nothing taken out, so this term will disappear. Okay. So, all of these are special case of these equations, and these equations in turn are special cases of the overall balance equation. Okay. These were the overall balance equation. Okay. PFR you obtain by saying d by dt is 0, this term is present, diffusion is 0, this term is present, and then this term things only vary in axial direction. So, you get d by dz of rho u omega k. Okay. You divide this by molecular weight, it becomes d by dz of u c k. Okay. So, PFR is a special case of species balance equation. CSTR also is a special case of a species balance equation. This term is not there, this term is not there because everything is well mixed, this term is not there, and there is reaction term, but this term gets replaced by in minus out boundary conditions. Okay. So, again I am not going to go over this, I am not going to, it is not there for exams or anything like that, but you can easily derive all of the reactors, CSTRs, batch reactor, well mixed reactors and all that as special case of this overall species balance. Okay. Yeah. So, we went over all of this. Okay. We recapped how you can do various math, and we talked about, you know, some shortcuts and which you can use. Okay. And the final thing is about equilibrium. I think that is all that. Yeah. Okay. This particular part I said that I am leaving it for your reference, for your self study, in the sense that, you know, complex problems involving batch, CSTR and PFR will not be there. Okay, but we cannot run a PG course in CRT saying that no, we are not going to talk about these reactors. So, for sake of completion, this part is kept. Okay, we will revisit this in module number 7 or 8. Now I do not remember. 8, module 8. We will revisit this in module 8. Okay, but again, all of these things that I talked about, it's all there. If you are to use conversion based approach or you are to use concentration based approach, the result is exactly the same. Okay. If it was a non isothermal system, we will come to that again in 8th module. You can simplify the overall equation irrespective of whether you use conversion based approach or a concentration based approach. Okay. Likewise, conversion based approach, concentration based approach for CSTR, conversion based approach, and so this is the overall derivation. And all that. Okay, this again, this is just for future reference. This is not something that we have done in module 1, 2, 3, 4, 5a. Okay. And the final thing is about equilibrium. Let us say you have a reaction okay. I am just making this up, okay, it is nothing, there is nothing really special about this. It's about the approach. Okay. Let's say we have, this is reaction 1, this is reaction 2, this is reaction 3, this is reaction 4. Okay, and I will make the arrows thick in the direction of forward. So, thick arrows is RF, thin arrows is RB. Okay. So, if you are to look at this circle, right. So, delta G2 plus delta G3 plus delta G4 will be equal to 0, because it is coming back to that same place. Okay. So, if you divide by RT or negative RT and then you take exponent of this, okay, you are going to get KQ2, K3, K4 equal to e to the power 0, that is 1. Okay. We will just use this shortcut. Okay. And we had gone over an example, and that example, I do not know, maybe I think it was ammonia only. Okay. Okay. This is how you had got that expression in your undergrad. Delta nu is 2 minus 1 minus 3, which is equal to minus 2, RT to the power minus 2. The only thing you have to be careful about is units. You have to use R in appropriate units. Temperature, of course, is in kelvins. which you can use mole fractions, yes. Okay. Again, I didn't remember this expression. I was just thinking in my head how it would look like. Why did it, how did you get this? Because P, partial pressure, is total pressure multiplied by mole fraction. Okay. So, you have total pressure multiplied by mole fraction, total pressure multiplied by mole fraction, total pressure multiplied by mole fraction over here to the power 2, power 1, power 3. P square P cube becomes P to the power minus 2 multiplied by Kx. That is how you get this. Okay. So, expand the answer to your question, there is no restriction about constant pressure, constant volume and so on. This is mathematically equivalent with no assumptions being made. Okay. Equilibrium is at the conditions in which equilibrium is calculated, which for a well mixed reactor will be outlet conditions, or for a batch reactor will be end conditions. So, if it is a system where pressure changes because of reaction, as pressure changes the equilibrium keeps nudging itself, and finally it reaches a case where pressure, temperature and species are all in equilibrium. Okay. Somehow we study that in, and phases are also in equilibrium. Okay. So, all of these analysis we can include phases also. All we have to do is pick the phase equilibrium and reaction equilibrium concepts from thermodynamics and just apply it at the appropriate places in your CRE. Okay. So, again, I mean, do not get confused. It can be confusing whether I should do it at initial condition, I could do it at final conditions, etc., etc. It does not matter whether you do it at initial condition or final condition, you need to go here and go there, whether you do it this way, whether you do it this way, it should be the same. Okay. When it comes to this specific analysis, I would suggest this way, because mentally it is more straightforward. Because if I do it this way, that means everything happens at inlet condition and then pressure changes to meet outlet condition. As pressure is changing, there is P total to the power minus 2. So, things will vary. Okay. Whereas, if you do it like this, things would have varied till you reach the desired pressure, and then the concentration will change to match it. Okay. Again, what all that means? Nothing. All that means is, when you looked at your ammonia reaction and you did equilibrium, initial was 10 10 0 or 10 20 0, extent was 5, so final was 5 5 10, and you did the equilibrium on 5 5 10. Okay, that is all I am saying. So, you will do the equilibrium on 5 5 10. If its constant pressure the volume would have changed to ensure that the pressure in 10 moles of gas would be same as what you started off with. If pressure is allowed to change, then the volume remains constant and the pressure drops, so that 20 moles occupy what the volume that earlier 30 moles was occupying. Okay, that is all there is. But what you look at, what did you do? You looked at the final. So, these were the number of moles. If it is constant pressure, I get mole fraction, multiply it with total pressure. If it constant volume, again take mole fraction, multiply with total pressure, but then the pressure had changed because of reaction, right? Include that and you are done. Okay, that is how you have solved the assignment problem. Okay, I am just saying that what you have done without realizing is exactly the answer to your question. Okay, the question was, you know, how is Kx and Kp related if it is a constant pressure system? The answer to that is Kx and Kp are related like this, irrespective of whether it is constant pressure or constant volume or any other system. Whether it is constant pressure or constant volume and all that is encountered in how pressure, volume and temperature are related to each other. Okay, and it is not really relevant in liquid phase system under typical operating conditions, reasonable pressures. Why? Because we assume volume does not change in liquids much. So, therefore, volume is not changing. So, concentrations are very straightforwardly connected to mole fractions. Okay, so that is all there is that is there. In fact, if for example, instead of doing a CSTR type of a thing, if you were to study detonation, or if you are going to study rockets, rocket launches or internal combustion engine, nothing changes from the reaction treatment point of view. What changes is how the cycles behave. So, for example, let us say it is a diesel cycle, remember first semester thermodynamics, right? It is diesel cycle. Where is the reaction taking place? No, no, reaction is taking place, no, reaction is, yes. Okay, so this is the reaction taking place. What happens during reaction? How does the pressure change during reaction? Reaction is this particular part, P total is coming from the diesel cycle. Okay. So, again the concepts that you are learning over here are not really all that limited to CRE. They are much broader than what we think. It is just that aspect is incorporated through pressure volume equations. And if we are only talking about equilibrium, combustion system we will not talk about equilibrium, because for example, methane combustion, the equilibrium constant is of the order of 10 to the power 24 or something like that. Okay, so or yeah, so which basically means that there is hardly going to be any methane molecule at equilibrium. Okay. Yeah, so that is that. Yep. Okay. Okay. Let us say that we have calculated our delta G's, assuming these are forward arrows. See, you are given delta G's. If let us say this was a more open ended problem, for example, my multi-scale modeling course, there you will actually calculate delta G's from heats of formation, enthalpy, entropy of formation and all that. There you get a choice which circle you select. Okay. So, anyway, your question. Hmm. 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 Okay. So, let us write this down. Okay. So, your backward cycle hmm. So, if you are following this arrow, it will just be negative of that. Okay. So, if you are saying okay, this direction is delta G2, this direction which is exactly what we wrote if we were to follow this. Yeah, I think what you are saying is if my delta G was defined like this, then what? Fine. In that case, if the delta G was defined like this, the way I am showing right now, your delta G2 will be equal to delta G4 plus delta G3. Okay, this new definition values will be negative of the old definition values, right? Okay. So, if the values are given to you, you have to just follow what is given to you. You can't say that I prefer to work it that way. Okay, but if heats of formations are given to you, an entropy of formation is given to you, you can choose which arrow you want to consider as a forward arrow. Okay. Yeah, I won't put this negatives here because otherwise. Okay, all of this I am not putting it online because suddenly in the flow of things you find one or two uh, slides coming in, you will get actually more confused. Everything that I discussed yesterday and today is all just a recap. Everything is already there in the 5 PDFs that have been uploaded. Okay, so don't be suddenly surprised that I don't know if you noticed or not. When I press escape, when it asks me whether keep annotations or discard annotation, I am clicking on discard today, unlike all other days. Okay, that's so that we don't get confused uh, with today's annotations. Okay, all that I did today is just a recap. I have not covered one single new concept. Okay, so we will just talk about, and again if you have noticed I clicked on don't save so that today's thing does not get saved. It will only be confusing, not that I have any problems sharing what I shared today. Okay. Okay. So, what we will do next time in the next class is talk about internal diffusion. Okay. We will go back to our this picture. Okay. What CSTR PFR talks about is flow and reaction. What we did in module 5 is 5A is external diffusion. What we are going to do in module 5B starting the next class is internal diffusion. what we did in module 4 is reaction on the surface. Okay. How this all is planned? Module 4 starts from the bottom, module 5 starts going towards the top, module 8 goes in the bulk. Module 5 is for gas solid catalytic, module 6 is gas fluid catalytic, module 6 is gas fluid non catalytic, module 7 will be gas liquid reactions or absorption, and then module 8 onwards we will again we'll get back to reactors. Okay. So, 1 and 2 was terminologies, recap, putting everything in context and setting up the stage. Module 3 and 4 were molecular, module 5, 6 and 7 are mesoscopic, module 8, 9 and 10 are reactor level. Okay. So, that is how the course is split up. And with respect to internal diffusion, what we are going to talk about, okay, is when we have a catalyst that is either a rectangular slab or spherical or cylindrical. Okay, in undergraduate I do not know if all 3 cases were done or one of these cases were done, but at least most of the students for slabs and for spheres everything was re-derived. We are not going to re-derive anything at all. We are going to look at our overall balance equation and we are going to knock off the terms that are not relevant. Okay. So, again undergrad bottom up approach, postgrad top down approach. We will assume that you are aware of the overall species balance and the overall energy balance equations, and the specific cases where we simplify those balance equations is what we are going to consider. Okay. Then we will talk about how diffusion happens within a pore. Okay. So, next lecture for the most part is going to focus on how diffusion happens in the pore. After that is our exam day, and after our exam we will skip all of these derivations and directly go to using this concept of what is called as Thiele modulus and overall efficiency factor. Okay. We will directly start solving a problem and then go to understanding the concepts. Okay. We are trying this out, hopefully that will help learning a little bit stronger, in the sense that we start off with definition, then once the definition and equations are there we directly solve the problem using them, and then we go on to how they were derived. Okay. So, just a change of strategy, this is based on feedback that you have given in the previous section.